Hello, space enthusiasts and curious minds alike. Welcome back to our channel, where we dive deep into the mysteries of the universe and the cutting-edge technology that helps us understand it. Today, we're tackling a groundbreaking story that's been making waves in the world of physics and astronomy. IT's GETT-INGWORSE. The James Webb Telescope has ended the debate in physics with its shattering images. Stick around as we unravel how these latest discoveries are reshaping our understanding of the cosmos. Assuming you're already familiar with the James Webb Space Telescope, I'll skip the lengthy introduction and dive straight into the heart of our discussion. Welcome to Territory, your gateway to space exploration. In the past 2 years, our understanding of the universe and its fundamental principles has undergone significant transformation, driven in part by discoveries made by the Webb telescope. These findings are setting the stage for even more astonishing developments in our comprehension of cosmology. Today, we're exploring some of the most groundbreaking theories put forth by scientists in the wake of Webb telescope's observations over these last 2 years. Theories that have the potential to radically alter our understanding of the cosmos. First up is the concept of a dark mirror universe. Dark matter, a mysterious and invisible force, remains one of the greatest enigmas in the field of cosmology. Yet, could it be that this phenomenon originates from a parallel mirror universe? A recent study suggests this is not only possible, but also provides compelling evidence to support such a theory. Intriguingly, for every pound of ordinary matter, there are 5 pounds of dark matter, which does not interact with light or ordinary matter. Our only means of detecting it is through its subtle gravitational effects. Let's delve deeper into this captivating subject. Despite their vastly different characteristics, the amounts of normal matter and dark matter in the universe are curiously similar, a fact that seems more than a mere coincidence. To unravel this mystery, researchers have begun to explore the potential connections between the two. They've proposed a theory suggesting that for every action involving normal matter, there's a corresponding mirror action in the realm of dark matter. This proposed symmetry between matter and dark matter could explain their nearly equal quantities. This theory also highlights another peculiar coincidence related to the physics of normal matter: the nearly identical masses of neutrons and protons. These masses are crucial for the formation of stable atoms, as even a slight increase in the proton's mass would lead to its instability, causing rapid decay and preventing atoms from forming. Such a universe would be dominated by free-floating neutrons. Scientists now theorize that in the dark matter's mirror universe, this alternate scenario might actually exist. In this parallel realm, the fundamental forces could render the dark proton less stable, leading to an environment vastly different from our own. In a universe where dark neutrons dominate, what we perceive as dark matter could be a mirror reflection of our own. According to current scientific understanding, the early universe experienced nucleosynthesis, a critical process where the universe's first elements were forged within a hot, dense state. If this scenario played out in the mirror universe as well, it's possible that connections between these two universes were established, allowing them to impact one another. By meticulously analyzing the rate at which elements formed a task for the James Webb Space Telescope and future observatories, scientists hope to uncover evidence of these inter-universal connections, offering us glimpses into the mysterious dark mirror universe. What are your thoughts on this intriguing hypothesis? If you're interested in a more detailed exploration of this topic, feel free to share your thoughts in the comments section below. But for now, let's shift our focus to another extraordinary theory: the concept of bubble universes. Emerging research from the University of Copenhagen and the Tokyo Institute of Technology introduces a fascinating idea. Our universe might be engulfing nascent universes, leading to its continuous expansion. This concept mirrors the way galaxies amalgamate, suggesting a cosmic process of expansion and integration on an unimaginable scale. This compelling theory draws parallels to the way galaxies merge to form larger systems or how black hole mergers result in supermassive black holes. It proposes a fascinating explanation for the expansion of our universe, suggesting that it grows by colliding with and assimilating smaller universes. This approach offers a fresh and intuitive perspective on dark energy, potentially aligning with observational data more closely than the conventional cosmological model. While the concept of a multiverse is not a novel idea, this research employs a mathematical framework to explore the implications of such universe mergers on our universe's evolution. The findings indicate that these mergers could account for not only the cosmic expansion, but also its accelerating rate. Moreover, this theory has the potential to address several cosmological puzzles. It posits that the rapid expansion observed in the early universe may have been triggered by our young universe merging with a larger parent universe. Following this significant event, our expanded universe continued to encounter and absorb other nascent universes. In a twist that could rewrite our understanding of the universe's origins, recent data suggests the possibility of not just one, but two Big Bangs. This theory introduces the idea of a parallel event, a dark Big Bang, that could be responsible for the influx of dark matter into our cosmos. Cosmologists are now considering that evidence of this dual event might be detectable through the examination of space-time ripples following the Big Bang. Traditionally, it's believed that the universe experienced a phase of rapid, significant expansion shortly after its inception, a period known as inflation. The catalyst for inflation remains a mystery, yet its existence is crucial for explaining various cosmic phenomena, including the universe's vast flat expanse on large scales. This phase is thought to have been propelled by an exotic quantum field that permeated all of spacetime. Following inflation, this field is theorized to have disintegrated, releasing a torrent of particles and radiation that led to the conventional hot Big Bang, marking what physicists often consider the universe's beginning. These particles eventually formed the universe's first atoms when the cosmos was still in its infancy. Just 12 minutes after its birth, the universe was already forming the precursors to stars and galaxies. Yet another component played a critical role in the cosmic equation: dark matter. The nature of dark matter remains one of cosmology's biggest enigmas, but its presence is inferred through its gravitational effects on visible matter. Initially, for simplicity, it was assumed that the end of inflation and the subsequent hot Big Bang were responsible for distributing dark matter throughout the universe, evolving on a path independent of normal matter. However, cosmologists now question this assumption due to a lack of direct evidence for dark matter's existence until much later in the cosmic timeline, well after it had sufficient time to impact the universe gravitationally. This suggests there was no need for dark matter to have been present in the same quantities as normal matter right after the hot Big Bang. Furthermore, considering that dark matter does not interact with normal matter in the same way, it could have experienced its own separate genesis, a phenomenon researchers are terming the dark Big Bang. In their innovative study, these scientists proposed the existence of a new quantum field, referred to as the dark field, which would be essential for facilitating the specific temporal boundaries to align with current dark matter observations. Too early, and the universe would be overrun with dark matter; too late, and there wouldn't be enough to account for observed gravitational effects. However, if this event transpired when the universe was younger than a month old, it would be consistent with all known data. At first glance, this hypothesis might seem overly ambitious, but it offers several compelling advantages. Firstly, it aligns with existing knowledge about dark matter's interaction, or lack thereof, with normal matter, suggesting they need not have originated simultaneously. Secondly, this theory allows for the development of dark matter models that do not interfere with early normal matter, providing researchers greater flexibility. Most intriguingly, The theory predicts a unique signature in gravitational waves, distortions in space-time, that continue to permeate the universe today. This suggests the potential for direct observational evidence of a dark Big Bang through the study of these waves. If the hypothesis that dark matter interacts with ordinary matter solely through gravity holds true, then the multitude of current dark matter experiments could be rendered ineffective. These experiments are based on the premise that dark matter and ordinary matter have some level of interaction beyond gravitational forces. Therefore, if this new theory proves accurate, the outcome could be quite disheartening. However, the theory suggests a fascinating phenomenon. As dark vacuum energy converted into dark matter particles, this transformation would have significantly impacted the fabric of space and time, leading to the generation of gravitational waves that permeate the universe. These waves could, metaphorically speaking, produce a continuous hum within the structure of space. Given that various astronomical events can create a similar background noise, the recent detection of such a hum does not directly validate this new theory. Yet, it introduces an intriguing possibility and opens a new path for exploration. The true test of this theory's validity over time remains to be seen. In an additional twist, cosmologists have discovered mature, ultramassive galaxies in the early universe, a finding that challenges the standard model of cosmology and suggests the universe may be older than previously thought. At an intersection of discovery that no one foresaw, the existence of massive celestial bodies presents a significant puzzle. They simply shouldn't exist in the form we're observing. These colossal galaxies, reminiscent of our own Milky Way and brimming with mature red stars, have been captured in stunning clarity by the Webb Space Telescope's deep field images. Spectral analysis reveals that these galaxies came into being astonishingly early in the universe's history, just 400 to 700 million years after the Big Bang. While the emergence of the universe's first star clusters not long after the cosmic dawn, a period marked by a universe awash in a thick hydrogen fog for the first 400 million years, was anticipated. The scale and maturity of the galaxies, observed through Webb's lens, defy expectations. These galaxies appear anomalously large, hosting stars that seem prematurely aged, existing millions of years before what our current cosmological models would suggest. This discrepancy points to a universe where, contrary to expectations, dark matter had not yet coalesced into the dense concentrations necessary to catalyze the formation of such massive galaxies. Moreover, these new observations pose a direct challenge to previous findings by the Hubble Space Telescope. For the ultramassive galaxies, identified by JWST, to have achieved such rapid growth, there would need to be an abundance of high-density regions in the universe's infancy, far more than previously believed. This revelation puts pressure on the standard model of cosmology, prompting a reevaluation of our understanding of the universe's early years. The recent discoveries have put the established cosmological model under unprecedented scrutiny, suggesting that these massive structures shouldn't have formed until a later stage in the universe's evolution. This has sparked a debate on whether it's time to rethink the prevailing theories, though not everyone is ready to discard decades of scientific progress. Julian Moose, an assistant professor of astronomy at the University of Texas and co-author of a paper examining potential modifications to the cosmological model, emphasizes the hierarchical nature of cosmic developments, starting from the smallest units to gradually building up to larger structures. Despite JWST's findings of galaxies akin to our own, but from a much earlier epoch, posing a conundrum, Moose and a team of astronomers from Johns Hopkins University argue that a complete overhaul of the standard cosmological model, even if it's not an outright replacement of the current model, the lambda, cold dark matter, CDM model, or the standard model of cosmology, enjoys widespread acceptance for its explanatory power, yet it is not without its limitations, especially when faced with observational challenges. Much of our understanding of the early universe remains theoretical, But with the advent of powerful observational tools like JWST, we're at a juncture where our theoretical frameworks may need to adapt to new empirical evidence. Leveraging the capabilities of the Webb Space Telescope, researchers have ventured deeper into the cosmic past than ever before, comparing its data with that from the Hubble Space Telescope. Focusing on a period 500 to 800 million years post-Big Bang, where both JWST and Hubble data overlap, scientists identified the heftiest galaxies observed by JWST and calculated the changes in the early universe's density that would allow these giants to exist. They also predicted how many smaller galaxies would emerge under these modified conditions. The expectation was that an increase in ultramassive galaxies would naturally lead to more smaller galaxies, explained Minas. However, the actual count of galaxies from Hubble during the same epoch didn't match their projections. This discrepancy suggests that simply tweaking cosmological models to account for the unexpected number of massive galaxies doesn't solve the puzzle, especially since Hubble's observations would have noticed these changes too. This conundrum brings researchers back to square one. Why is JWST finding so many ultramassive galaxies? One theory posits that these galaxies could harbor supermassive black holes. The intense heat from these black holes could make surrounding gas glow more brightly, making the galaxies appear more massive than they actually are. This could explain their apparent prevalence without necessitating a fundamental overhaul of cosmological theories. Another hypothesis is that these galaxies might not actually hail from the early universe, but seem to be because of dust that reddens their light. As light travels through space, it stretches and shifts to the red end of the spectrum, potentially making galaxies appear more distant than they truly are. However, with the Webb Telescope, we are observing galaxies that formed as early as 320 million years after the Big Bang, during what is considered the cosmic dark ages, a period lasting from about 350,000 to 1 billion years post-Big Bang. If these galaxies had ignited within this time frame, the dense hydrogen gas surrounding them would have absorbed their light, preventing it from reaching us. Despite this, Webb's observations suggest we can still see these galaxies, indicating their light has successfully traversed the cosmos to reach us. Furthermore, upcoming data from ongoing galaxy surveys conducted by the telescope are anticipated to push these observations even further back in time, unveiling galaxies from even deeper within the cosmic past. Our own Milky Way, aged at 13.6 billion years, is not classified as ultramassive. It is expected to become one of the largest galaxies in the local group following its eventual merger with the Andromeda Galaxy in about 5 billion years, illustrating that galaxy growth to ultramassive status takes considerable time. Yet, Webb has identified galaxies that seemingly achieved this scale much earlier in the universe's history, challenging our understanding of galaxy formation and evolution. Astronomers are planning to adjust the Webb telescope's mirror to focus on these intriguing galaxies, aiming to gather their light spectra for detailed analysis. This process will allow them to dissect the light into its component wavelengths, providing insight into the galaxy's chemical and physical characteristics. For the first time, we peered into the very early universe, uncertain of what we'd uncover, shared a scientist from Penn University. Remarkably, we encountered phenomena so unforeseen they challenge our scientific understanding, raising questions about our theories of early galaxy formation. This discovery prompts us to consider whether the universe might be older than we thought, and suggests we might just be beginning to unravel a mystery far more profound than previously imagined. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, You will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.